Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius Podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy of my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out. And I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition, or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on current initiatives. And now to our guest.
Hello, this is Richard Jacobs with the Finding Genius podcast, part of the Finding Genius Foundation. Quick note about the foundation. We started on our project to create an AI-powered guide for people suffering from anxiety and depression. We call it Samwise. And Samwise is going to be fed about 5,000 sources of material, from lectures to books to peer-reviewed papers. And the goal is to create a low or no-cost resource for people suffering from anxiety and depression. If you have any interest in this, we do need help with donations and volunteers. Go to findinggeniusfoundation.org. So today, my guest is Yibin Kang. He's a Warner-Lambert Parke-Davis Professor of Molecular Biology. And we're going to talk about cancer and metastases. So Yibin, thank you for coming.
Thank you, Richard.
Well, tell me a little bit about your background. How did you start to work in cancer biology, and what were you doing before?
I came originally from China. I did my undergraduate study at Fudan University in Shanghai, and then I came to the United States after college and went to Duke University to study for my PhD. At Duke, I actually didn't study cancer. I studied virus, how virus interact with the host in order to replicate. So it's viral-host interaction studies. And then for my postdoc, I decided to take on a more probably complicated question of how the tumor interact with the host tissue to metastasize. And that's why I went to Memorial Sloan Kettering Cancer Center in New York and worked with Dr. Joan Massinga to study cancer metastasis.
Okay, and you've decided to focus in on, what's your current research now? Is it about cancer metastases, or what's it about?
Yeah, so I came to Princeton in 2004 after I finished my postdoctoral research. And during my postdoc, I mostly focused on breast cancer metastasis to bone. And after I set up my lab at Princeton, we still study the main question of how does cancer spread, metastasize, because that's how people die from cancer. But I came to the realization that when people die from metastasis, it's not like the last moment that metastasis happened. It's a final kind of manifestation of many things that happen throughout the evolution of cancer. And many of them actually happen relatively early, before even the patient know they have cancer. And so my lab over the years have evolved after we started in Princeton more than 70 years ago to basically study a pretty broad spectrum of the tumor-host interaction from the early stage of even before cancer happened, how the normal mammary gland stem cell use the niche component to maintain their stem cell activity, and then how that goes wrong to drive the breast cancer formation. And some of the events that happen here early in tumorigenesis also is relevant to how they metastasize. So a lot of our study is about this holistic understanding about how the tumor adapt as they progress and eventually leads to the metastasis.
Do you think that, is it possible that all cancers metastasize? We just can't see it. So we think we only see a primary, but in effect, there is some low level of metastasis going on in every cancer, or no?
It's a good question. Actually, it probably varies depending on the cancer type. Some of the cancers like glioblastoma, which is highly aggressive, very invasive in the brain, almost never metastasize outside of the brain. But there are a lot of cancer that metastasis probably happen much earlier than we know. Like, for example, breast cancer. A lot of the breast cancer patients are diagnosed with stage 1 localized disease, and they have surgery, and they are supposed to be clear of cancer. But then, a few years or even decades later, they have a relapse that is happening not in the breast, but in the bone or in the lung or in the liver. And so it's clear that those tumors escape early and just remain dormant for a very long time. And later on, something happened that they emerge as metastasis.
Well, possibly maybe a different thought about it. I've interviewed people that say that it seems like cancer tumors communicate through extracellular vesicles. So it's not, I don't think it's like primary is the mother tumor and then it directs or guides the other ones, but it does seem that they form with metastases a diffuse network of tumors that communicate. If someone has what appears to be localized disease, let's say breast cancer, you cut out the tumor, you do surgery on the breast, perhaps that communication link is severed, and that causes the existing metastases that weren't found to then take a different path because they're not getting that signaling. And perhaps that's what causes, downstream later reoccurrence.
It could be. There's a lot of theories about how actually sometimes treatment could disrupt the equilibrium or some kind of communication. Some of the early work by Judith Folkman at Harvard shows that in some mouse model, but also in human patients, that incidentally it happens that when patients have their primary tumor removed, the metastasis kind of just slow. And part of the reason in his study shows that the primary tumor release this so-called angiogenesis inhibitors that suppress the blood vessel formation in metastasis in distant organs. And so when you remove the primary tumor, those angiogenesis inhibitor is no longer there in circulation. And all of a sudden, those dormant micrometastases start to grow blood vessels and start to grow out of control to become clinically observed metastasis. And so that's just one of the theories. There are many other things that happen, in the systemic level. Communication-wise, there are already a lot of evidence that primary tumor release those vesicles that, so-called exosomes that you mentioned, that could be either promoting the formation of niche, promote metastasis, or suppress the niche formation. And so we still don't know exactly how that happens in different cancers. And there's a growing field called liquid biopsy that is maybe trying to tackle that question of, instead of doing this needle biopsy of the tumors, taking a snapshot of the tumor, the liquid biopsy maybe give you a more comprehensive understanding about what's going on in the whole body, in the circulation, but also, for example, circulating the DNA, circulating RNA, circulating vesicles. That is almost like a climate happening, with all those factors that could be influencing.
Has anyone done the following experiment? Let's say I take 50 mice and I, give them cancer of a type that, is known to metastasize. And I take half the mice and I do surgery and I resect the metastases, but leave the primary. And the other half of the mice, I resect the primary and leave the metastases, and then compare the outcome for the mice. Has anyone done that?
Yeah,
and seen a difference?
That's exactly what Judith Folkman did. And they use a cell line called Lewis lung carcinoma. It's a lung cancer cell line. And that's why they observed, this interesting phenomena that when they resect the primary tumor, the metastasis just kind of grow out of control. But, it doesn't happen all the case. I will give a word of caution that a lot of this model system, is very dramatic in mouse models, but it doesn't necessarily mean it's happening in the patients that, definitely in patients who have cancer, they should have surgery to remove it for sure, because you don't want that to be growing. But we do need to take into consideration that it is a systemic effect. And maybe it's a better way is to consider those factors so that when you intervene with either surgery or radiation or chemotherapy, you reduce those risk factors that are unintentionally caused by those interventions.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
If we understand the biology.
Okay. So again, you saw when they resected the primary, now the signaling probably appeared to be screwed up and the metastases went crazy and became more aggressive. What about in the other version where they took out, one or more metastases but left the primary? What happened then?
That's a good question. I don't think that that opposite experiment. Typically, those type of experiments are harder to do, to remove the metastasis and keeping the primary growing. There are a lot of technical aspects that only one is the metastasis is harder to remove surgically, clinically, and second is usually there's a lot of guidelines regarding the certain type of experiment you need to do, and you cannot do or need to do. For example, the primary tumor, when they grow to a certain size in mice, you have to remove it for ethical considerations. So there are some limitations that perhaps cause the opposite experiment that you suggest. I don't think they did that exact experiment that you suggest.
Okay. When you mentioned earlier, and I've heard this a lot, it's metastases is what kills somebody. Can anyone tell which metastases kill somebody? Or is it that you have now such a tumor burden in different organ systems, that's what kills you? It's the sum total of all the tumors? Like, what is the mechanism? I know it's a terrible thing to ask, but what has been postulated or observed as the mechanism of death when people have metastatic cancer?
Right. So the death from cancer could be very complicated. Eventually, metastasis kill patients, but it could be due to various reasons. For example, if tumor metastasizes to the brain, because brain have this physical hard space that there's only certain room for the tumor to grow, and when they cause this compression on the nerve and the brain, and it will eventually disrupt the function of the brain and then cause the death of patient. And same thing happened with lung and liver. It's an organ failure that patient just failure of key vital organ that leads to death. And sometimes it's a more complicated factor. For example, metastasis to bone in the spinal cord that could cause, for example, hypercalcemia, that sometimes could be life-threatening. And also because the bone is the blood, generating organ. So the red blood, white blood cells are produced in the bone marrow. And so when the tumor grows in the bone, that also basically disrupt your immune system to function properly, to generate the platelets to, avoid stroke and, blood clotting and, those kind of also fighting the infection. So sometimes people actually die from infection because their immune system is weaker. And sometimes they just die from cachexia, the wasting, of muscles and just become very weak. And so there's a variety of factor. One could be more local organ failure, and some could be more systemic, like the weakened immune system or, hypercalcemia or, infections and things like that.
Has anyone, I guess you'd have to do this in mice for a start, but has anyone been able to get a estimate of the number of cells in, let's say, a mouse liver, then infected with cancer, let the tumor grow to a substantial size, then reassess the number of cells or the volume or the weight of the liver? The reason I'm asking is that no one's confirmed this, but does cancer co-opt healthy cells and turn them cancerous, or does it just grow from its own cancer cells? And again, an organ that has this disease, this tumor burden, does the organ get heavier and bigger, or does the tumor just grow and the organ doesn't change size, but the tumor pushes everything out and physically elbows everything out of the way and obstructs the functioning of an organ?
Typically, when the organ becomes affected by cancer, it does get bigger. That's actually one of the ways we measure the tumor burden in the mice. Is, for example, when they develop the lung cancer or lung metastasis, simply by weighing the weight of the lung after necropsy, you could kind of estimate the tumor burden, because it's just the tumor just become, the bulk of the tumor, and they just keep growing. And, sometimes those mice look completely fine, and then the next second they just drop dead because they just run out of lung cells to produce the, to allow the oxygen to be passed. And so, yeah, so indeed, that when like same thing with the liver, for example, when they grow in the liver, they become huge. They replace the normal tissue, replacing the normal tissue functions.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
Okay, so the organ does get heavier, but the increase of size or heaviness, it's all from tumor? Yes. Or does it also somehow cause the regular cells to grow too?
Typically, they don't so-called transform a normal cell to become cancer cells simply because they are cancer cell nearby. Because usually the tumor produced factor is not enough to transform a normal cell completely to be a cancer cell. But it doesn't mean they will have influence. Sometimes they will cause this reaction to the tumor that also contribute to the growth of the mass. For example, some of the cancer, actually, when you look at it, more than half of it, actually sometimes even 90% of it, are not tumor cells. It's just like a lot of the so-called fibrosis, the hardening of tissue because of the fibroblast, the spindle shape, those,
Wait a minute. So you're saying an average tumor, a lot of it is like fibrous tissue? It's like a scaffolding that cancer cells nest in?
Yeah, so fibroblasts, and there's also a lot of immune cell, So immune cell, you can imagine when there's something going on, there's an inflammation. So cancer is often called a wound that never heals. Like it's like an ulceration. It's the inflammation that is continually going on. And the tumor tries to repair the damaged tissue, but it couldn't do it. It's basically all messed up, and so the immune cell keep coming in, and then they are under the influence of tumor, right? So, for example, the fibroblasts usually is good. They help us repair the cut tissues and things like that. But the fibroblasts under the influence of cancer, they become carcinoma associated fibroblasts, so-called CAF. They become kind of change in their property, and they become, for example, they become more migratory. They produce a lot of the so-called extracellular matrix, and they produce a lot of inflammatory factors, and that attract even more immune cells. And the immune cells come in, they become changed. They change from cancer-fighting immune cell to become immunosuppressive immune cell, and that causes the immune system coming in but not able to fight off the cancer, and instead just contribute to this continuous growth of cancer. So, you can imagine it's as if like you have a city, right? And everything works well. You have the police system, you have the judiciary system, you have the plumbing, you have the traffic, right? It's like New York City. But then, something goes wrong and it becomes corrupted. And so supposedly the immune system, the police is supposedly catching the bad guys, they become corrupted and they become helping those criminals. And, the firefighters come in, they try to put out the fire, but instead they cause more flooding. And the drainage system, the lymphatic system is blocked, so they cannot drain. And then the tumor become very high pressure in terms of fluid pressure. And so, like it's a city that is falling apart. You can think about it that way, right? And so cancer is really not a tumor. It's not just the business of tumor. It really is a corrupted system that the tumor hijack a normal functioning bureaucracy and turn it against our own body.
Yeah, that's really interesting. And I see why some people say cancer is a wound that never heals, because, if you have a heart attack, you'll get, fibrosis in an attempt to heal. That's kind of, yeah. So, okay, so the body, it looks like perhaps is perceiving cancer as a wound, and that's why it's sending fibroblasts to, to try to fix and repair, and sending immune cells to try to get rid of it, which get co-opted. That's really interesting. I didn't know that. So what percentage of a tumor's mass is cancer cells versus fibroblasts and immune cells? Has anyone looked at the ratios, and does that tell you anything?
Yeah, it varies a lot. Some of the cancer type is, I think it's very typical to see a cancer that is over 50%. non-cancer cell. It's typical breast cancer. If you do a core biopsy, you probably see about 50%, between 30 to 60%, so it's you get all kind of like immune cells, fat cells, nerves, and blood vessels, and neural cells, and things like that. And they're interestingly, they all participate in the progression of cancer one way or the other.
If I assume cancer is a spheroid, and I cut into it, and I look at the center versus the middle versus the outside, how does that composition change?
That's a good question. Usually, a lot depends on the blood supply, right? So very typical is in the core of a tumor mass, a circular, tumor. The middle of it is usually necrotic, meaning that the cancer is dying inside because they just run out of blood supplies, and they are hypoxic. They lack the oxygen, and so you see a lot of necrotic cells. Basically, the cells, they are dying. But in response to that hypoxic condition, the tumor also undergo a lot of changes. They start to produce a lot of factors that try to increase angiogenesis, the blood generation. And the tumor cell themselves also undergo changes. For example, they can undergo a process called epithelial to mesenchymal transition. So a lot of cancer, 80% of cancer are so-called carcinoma because they are from so-called surface cell, the epithelial cell lining the surface of our skin, surface of our mammary ducts, or the prostate, or the guts, and they change to become more fibroblastic, more motile, and so it's called EMT, epithelial mesenchymal transition. So in the periphery of the tumor, you probably see those type of cells. In the periphery, you probably see more immune cells in the periphery, and then in the middle of it, because of the hypoxia, a lot of the immune cells are probably also dying in the middle as well. So in different kind of cross-section, different depths, you will see different activity and property of tumor and stromal cells.
If you study the outside surface of a tumor, what does that look like? Is it kind of, is it porous? Are there a lot of areas that are, I guess, that become fibrous that nothing passes through? Like, what does the structure of the surface of a tumor look like? Has anyone looked?
It also depends on the kind of tumor you're looking at. There's different stage, different grades. A lot of the more early stage tumor, there are better prognosis, meaning that after the patient have surgery, they are more likely to survive. Long term is they are surrounded by this so-called ECM, extracellular matrix. It's almost like an encapsulated tumor, and usually there's a kind of basement membrane surrounding the tumor, and surrounded by ECM, and you could have a more clean surgery to have a clean margin after surgery. But some of the more invasive tumor will have a lot of infiltrations of tumor. It's almost like the crab. That's why cancer is called cancer, because the Greek described them as crab. They are like extending those legs out through a process of invasion. So the tumor will invade through the basement membrane. They invade through the muscle layers, fat layers, and then get into blood circulation. So then the border becomes unclear between the tumor and the surrounding tissues. And when you try to do a surgery, it's harder to get a clean margin. You might left over some tumors that already, it seems to be distant from the core of the tumor, but they already infiltrate, into surrounding tissues as, kind of extending arms out. So that often give you a indication that this is a highly aggressive cancer. And those patients are likely to detect tumors in circulations or in the lymph nodes, and they have a high risk of recurrence.
What about the structure of metastases versus primaries? Is it same, heterogeneous structure where it's kind of a mess, or do they have different structures?
Yeah, it probably varies depending on different organ size. And oftentimes when the tumor first disseminate, they exist as sometimes even like single cell or small nodules, like those small little clusters that are nested in certain niche component. And this is actually interesting, intriguing. One of the ongoing research hot topic in the field is when tumor disseminate, is it completely random? They just like lodge in blood vessels and they just grow out whenever they get lodged. Or they favor certain kind of niche for survival or for dormancy or for outgrowth. And so there's a lot of exciting research recent years because we have some really cool technology now to be able to trace those cells that are disseminated from tumors and mark them, and also mark the stromal cells that are surrounding them. And then not only that, we can now do a lot of this, for example, single cell RNA-seq to identify what kind of cells they are and what kind of genes they express and how they communicate with tumors. Because when you think about it, this is actually the best window to have a cure of the patients is after they have the surgery to remove the primary tumor. And in this window, before they have any overt relapse happen, that they have a window to wipe their system clean, to eliminate those disseminated tumor cells. And if you can do that successfully, you have a cure. And the question is, how do you figure out to do that successfully? You need to understand what kind of niche they interact with and what kind of factors they rely on. And so this is actually one of the also kind of ongoing research in my lab is to understand, what make a tumor cell survive under favorable conditions when they spread, in circulation or when they get to a distant organ. And because I think that gives us the best chance of offering an effective cure for the patients.
Could anyone mathematically model how a tumor started? If you look at the heterogeneity of it and the structure of it, could you back calculate what it looked like at an earlier stage or at the beginning?
There are actually a lot of mathematicians try to model tumor cancer progression mathematically. You could, I'm not a mathematician, but, at Princeton, I do collaborate with people in mathematics department and try to deduce some of it's hard to model the whole process of cancer, but at least you can model some of the process. For example, this epithelial-mesenchymal transition that I mentioned to you earlier, how the cells change their cell property to try to migrate. When they try to do that, you can follow a mathematic, relatively straightforward. It's never simple with mathematics, but you could model them with a number of differential equations, and then to see how there are certain behaviors that you could predict from mathematical modeling. And then we can test that in the laboratory. They actually give a lot of insights that we, as biologists, wouldn't naturally think of. For example, what we understand from those modeling is that the cell seems to have a memory, like when they disseminate from the primary tumor into circulation, and when they undergo this EMT, epithelial-mesenchymal transition, they have to be under the stimulation of certain factors. But what the model turns out is that they don't have to be under that influence permanently, throughout the journey to distant organ. As long as they are exposed to those factors, like factor called TGF-beta, for only a few minutes, is enough to give the cell a memory to allow this process to happen in the next 3 days. And that's actually a very important insight to get to understand how to therapeutically target this process. So there's a lot of room for mathematicians and engineers to step into the field of cancer research and try to model it, or, for example, develop device like this lab-on-chip device to mimic, for example, circulation and mimicking tumor interacting with the stromal tissues in distant organs, and that allow mathematical calculations of these interactions, and eventually we could try to extrapolate and try to see if we can see the same thing happening in the model in mice or in the human patients.
So what are some of the important questions that you're trying to answer with your research?
Yeah, so actually some of the most exciting research that we did, there's a couple of papers coming out next month, is regarding one of the intriguing questions we have been always asking is, oftentimes you have two patients coming into hospital. They both have breast cancer, both have the same stage of cancer, stage 1, and yet oftentimes they have very different outcomes. One patient will have surgery and will be cured, and nothing happened after that. And another person will have a relapse, a metastasis, and that is resistant to treatment, and then eventually die within a couple of years. And so they so-called poor prognosis tumor that is really bad in terms of outcome. And there's also tumors that are less aggressive, so-called good prognosis tumor. And this actually has been puzzling in terms of what really is the reason behind that. And, can we predict certain tumor to be likely to be bad tumor? And not only that, can we therapeutically intervene? Because patients don't want to be told that you have a high-risk cancer, and you are likely to develop metastasis within the next 5 years. Imagine they have to live with that every night, going to sleep. And so we actually have been working on this question in the last 15, 17 years. And interesting finding is that oftentimes biologists tend to classify cancer-relevant genes as oncogene that drive cancer or tumor suppressors. And we know, some of the famous ones. BRCA1 is a tumor suppressor in breast cancer. But there's actually another category that we like to call so-called cancer fitness gene. And one of the examples is coming out in one of the studies we are publishing. What are the cancer fitness genes? These are the genes that themselves could not cause cancer. They are not oncogenes, right? But they are essential for the cell to survive and thrive under stressful conditions. And why is that important? Because when the cancer progresses from primary tumor and eventually to metastasis, they are undergoing a higher level of stress. They are all different kind of stress, like the hypoxic stress that I mentioned earlier, the metabolic stress. They have access to different kind of nutrients, and there's mitotic stress because they replicate a lot. All kind of different stress that they have to deal with. Those stress that are not normally encountered by our normal cells in a healthy person. And so the so-called fitness genes are the ones that is really not important for normal cells to function normally, but really critical for cancers to survive. And they become critical for cancer. And when you think about it, these should be ideal targets for therapeutic intervention because it's unlikely to cause severe side effects if you block them. But it will cause the cancer to become vulnerable again, either by
Are these always existent? They're just upregulated or, epigenetically allowed to express themselves more?
Yeah, so a lot of them, these fitness genes are epigenetically upregulated. They become higher. We often see them become highly expressed as the cancer progresses to a higher grade, higher stage, and to metastasis. It's an indication that this is clinically driving cancer progression. And so it turns out that some of those genes make a lot of sense because one of these genes that we are studying is causing the cancer to downregulate their antigen presentation. Antigen presentation is very important for the immune system to recognize that this is a cancer cell and to attack. And so by suppressing their antigen presentation system, the cancer basically becomes invisible to our immune system. And so, normally in a normal cell, this is not that important because our immune system recognizes our own cell as ourself, so we don't attack them. But the cancer, because they have a lot of mutations, they will present those as mutations, as non-self, and they will be attacked by the immune system. And so they come up with this way to suppress the immune antigen presentation and to escape that immune surveillance. And so these are just some of the, for example, they are fitness genes that cause the cancer to adapt to oxidative stress better. Again, those are kind of stress that our normal cells don't experience a lot. So I think these are some of the exciting directions that we're going, is to identify those so-called cancer fitness genes and to also at the same time develop therapeutics. In the same study, we also developed small molecular compounds that target the gene, and we show that it does show therapeutic benefits, at least in the mouse models. And so I think there's a lot of opportunity. One is to understand the biology, to identify those fitness pathways, and then to therapeutically intervene. And we already have success stories. In the realm of cancer therapy, immunotherapy is really not targeting oncogenes. They are targeting the cancer fitness gene, the system that inactivate our immune system. And now we are reactivating the immune system. And that is perhaps the pathway to potentially the way for a cure for cancer, is using our own living drug system, the immune system, and find ways to activate that.
Well, very good. Yibin, I learned a lot from talking to you. Great call. What's the best way for people to find out more about your work? Where can they go?
You could follow me on Twitter. My Twitter is just Yibin Kang, easy to find. That's probably the easiest way. You can also just Google my name, because there's only one Yibin Kang you can find online.
Yibin is Yibin, right?
Yes, and then Kang is Kang. Yes.
Okay, Yibin. Thank you very much for coming. I really appreciate it.
Thank you.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.